Industrial air compressors, a case study on Ingersoll Rand maintenance and repair. Chapter 1. General information about industrial maintenance. Mechanical, electrical, hydraulic. Industrial maintenance is a critical discipline focused on ensuring the reliable operation of machinery and equipment in manufacturing and production environments. It encompasses a proactive and reactive approach to preserving assets, minimizing downtime, and extending the lifespan of industrial systems. At its core, industrial maintenance involves monitoring, servicing, and repairing components across three primary categories: mechanical, electrical, and hydraulic. Mechanical maintenance deals with the physical moving parts of machinery, such as gears, bearings, belts, and pumps. This includes routine inspections for wear and tear, lubrication to reduce friction, and alignment checks to prevent vibrations or imbalances. Common issues like misalignment or bearing failure can lead to catastrophic breakdowns if not addressed, emphasizing the need for predictive techniques like vibration analysis. Electrical maintenance covers the power and control systems, including motors, wiring, switches, and circuit breakers. It involves testing for voltage stability, checking connections for corrosion or looseness, and ensuring compliance with safety standards. Electrical faults, such as overloaded circuits or faulty contactors, can cause shutdowns or hazards like fires, making regular diagnostics essential. Hydraulic maintenance pertains to fluid-based systems that transmit power through pressurized liquids, often used in actuators, cylinders, and lubrication circuits. This includes monitoring fluid levels, filtering contaminants, and checking seals for leaks. Issues like fluid degradation or pump failures can reduce efficiency or cause system overheating. Together, these areas form a holistic maintenance strategy, often guided by programs like preventive maintenance schedules or condition-based monitoring, to keep industrial operations running smoothly and cost-effectively. Chapter 2. General Introduction to Industrial Air Compressors. Brief history: what are they used for? Industrial air compressors are essential machines that convert power into potential energy stored in pressurized air, serving as a vital utility in numerous sectors. Their history traces back to ancient times, beginning with human lungs as the earliest compressor for blowing air into fires. Around 1500 BC, the invention of bellows marked the first mechanical advancement, providing concentrated blasts for metallurgy. By 1762, John Smeaton introduced water wheel-driven blowing cylinders, replacing bellows. In 1776, John Wilkinson's blasting machine became a prototype for modern compressors, and by 1829, the first compound air compressor was patented, enabling multi-stage compression. The Industrial Revolution accelerated their evolution, with compressors powering tools in factories, mines, and construction. The 20th century saw innovations like rotary screw and centrifugal designs, improving efficiency and reliability. Today, companies like Ingersoll Rand, founded through mergers in the late 19th and early 20th centuries, led in producing advanced models. Air compressors are used for a wide array of applications, including powering pneumatic tools, spray painting, sandblasting, and operating HVAC systems. In manufacturing, they drive assembly lines; in healthcare, they supply medical air; and in energy sectors, they support drilling and pipelines. Their versatility stems from providing clean, controllable power without the risks of electricity in hazardous environments. Chapter 3. Introducing Ingersoll Rand's 0 Hz air compressor that we are fixing. The focus of our repair project is the Ingersoll Rand R Series 37 to 45 kW, 49-60 horsepower, oil-flooded rotary screw air compressor, configured for 50 Hz operation. This model is designed for regions with 50 Hz electrical grids, such as Europe, Africa, and parts of Asia, including Algeria. It delivers reliable compressed air with capacities up to 8.5 cubic meters per minute at pressures of 7 to 10 bar, making it ideal for industrial applications like automotive manufacturing, food processing, and general plant operations. The R Series incorporates advanced features like a progressive adaptive control system for energy efficiency, a robust air end for durability, and integrated variable speed drives in some variants to match output with demand. R-specific unit, installed in a workshop in Algiers, had been in service for several years, providing compressed air for tools and machinery. However, it recently failed to start, prompting our troubleshooting and repair efforts. This compressor exemplifies Ingersoll Rand's commitment to time-proven designs enhanced with modern technology for high reliability and productivity. Chapter 4: Introducing Mechanical Parts and Troubleshooting. The mechanical components of the Ingersoll Rand R-Series compressor form the core of its operation, including the air and rotor assembly, belts or direct drive couplings, inlet filters, and discharge valves. The air end consists of two intermeshing rotors that compress air as they rotate, sealed and lubricated by oil. Other key parts include the cooler for heat dissipation, the separator tank to remove oil from compressed air, and the minimum pressure valve to maintain system pressure. Troubleshooting mechanical issues begins with visual inspections for leaks, unusual noises, or vibrations. Common problems include clogged air filters reducing intake, worn bearings causing grinding sounds, or misaligned belts leading to slippage. For instance, low air output might stem from a dirty inlet filter or a faulty unloader valve. To resolve, clean or replace filters, realign belts, and check rotor clearances. As shown in the schematic below, which illustrates side, front, and top views of the compressor assembly, the mechanical layout highlights the air end's central position connected to the motor via a coupling, with airflow paths from inlet to discharge. Chapter 5: Introducing Electrical Parts and Troubleshooting. The electrical system powers and controls the compressor, comprising the motor, typically a three-phase induction type, pressure switch, contactors, overload relays, and wiring harness. The motor drives the air end, while the pressure switch monitors tank pressure to cycle the unit on and off. Control panels include circuit breakers for protection and sensors for monitoring temperature and pressure. Electrical troubleshooting involves checking for power supply issues, such as tripped breakers or voltage fluctuations. Faulty wiring can cause intermittent operation, while a bad contactor might prevent starting. Overheating motors often result from overloads or poor ventilation. Solutions include testing continuity with a multimeter, replacing faulty switches, and ensuring proper grounding. The wiring diagram below depicts a typical setup, showing connections from the power source through the MCB, miniature circuit breaker, overload relay, and to the compressor motor, with a DP switch for manual control. Chapter 6: Introducing Hydraulic Parts and Troubleshooting. In the context of rotary screw compressors like the R-Series, the hydraulic aspect refers to the oil lubrication and cooling system, which uses pressurized oil, a hydraulic fluid, for sealing, cooling, and lubricating the rotors. Key components include the oil pump, filter, cooler, thermostat, and separator. Keel circulates through the air end, absorbs heat, and is then separated from the air before recirculation. Troubleshooting focuses on oil-related issues, such as low levels causing overheating or contamination leading to varnish buildup. Common problems include clogged filters reducing flow, leaking seals, or a malfunctioning thermostat bypassing the cooler. Excessive oil carryover into the air might indicate a faulty separator or high oil levels. Remedies involve changing oil and filters regularly, checking for leaks, and ensuring proper oil type, e.g., Ingersoll Rand's Ultra Coolant. A schematic of the oil system would typically show the flow path, from the sump through the pump, filter, air end, cooler, and back to the separator. Unfortunately, a specific image is unavailable, but visualize a loop with the air end at the center, oil entering to lubricate rotors and exiting to the cooler for heat exchange. Chapter 7: Finding the Problem: Electrical Wiring Being Twisted Wrong. After initial diagnostics, we isolated the issue to the electrical system. The compressor failed to start, with the motor humming briefly before the breaker tripped. Inspections revealed no mechanical binds or hydraulic leaks, but electrical tests showed irregular voltage drops. Upon closer examination of the wiring harness, we discovered that several wires in the three-phase connection to the motor were twisted incorrectly. Specifically, the phase wires were crossed, leading to an improper rotation direction and phase imbalance. This twisted wrong configuration caused the motor to draw excessive current, overheating the windings and triggering the overload protection. The misalignment likely occurred during a previous maintenance attempt or due to vibration loosening connections over time. This prevented the compressor from building pressure, halting operations entirely. Chapter 8. Fixing the problem. To resolve the issue, we first de-energized the system and locked out the power source for safety. We disassembled the wiring panel, untangled and correctly reconnected the phase wires according to the manufacturer's diagram, red to L1, yellow to L2, blue to L3, with proper grounding. We used torque wrenches to secure terminals, preventing future looseness. After reassembly, we tested continuity and insulation resistance to confirm no shorts. Powering up, the motor started smoothly in the correct direction, and the compressor built pressure without tripping. We monitored for an hour, checking temperatures and currents, and performed a full system flush to ensure no secondary damage from the fault. Chapter 9. Reflecting on the journey and what we learned. This repair journey underscored the interconnected nature of industrial maintenance, where a seemingly minor electrical oversight can disable an entire system. We learned the critical importance of following schematics precisely during interventions and conducting thorough post-maintenance tests. It highlighted how mechanical, electrical, and hydraulic oil systems must align for optimal performance, reinforcing the value of integrated troubleshooting. Personally, we gained deeper appreciation for preventive measures, like regular wiring inspections and training on phase sequencing. This experience not only restored the Ingersoll Rand compressor to full functionality but also enhanced our skills, ensuring safer, more efficient operations in the future. Industrial maintenance is as much about learning from failures as preventing them.